Hey guys, welcome back. In today's lesson, we're going to learn how to name binary acids and bases. This is a super common topic that confuses a lot of students, but I promise by the end of this video, it's going to feel so much easier. So first things first, binary acids in their natural gaseous state are named using the same rules we used for naming binary compounds made up of two nonmetals. The only difference? We do not use prefixes here. So no mono, no di, no tri, no tetra for indicating the number of atoms present in a compound. We don't use any of those for this rule. And let me show you an example. Let's say you have HF gas. That's what this G means. It means that it's a gas. The first element is hydrogen, so the first name stays the same. The second element, fluorine, you change the ending so it becomes fluoride. So, putting it together, we get hydrogen fluoride. And this is a binary compound made up of two different elements, hydrogen and fluorine. And because it's a gas, we use the naming rules for covalent binary compounds. But again, remember, no prefixes. It's not hydrogen monofluoride, it's hydrogen fluoride. And honestly, if you haven't done so already, I highly recommend you check out my last video where I talked about naming covalent compounds and ionic compounds. So definitely give that a try when you get a chance. Now, what happens when you take hydrogen fluoride gas and you dissolve it in water? Well, now things change. You see, when you dissolve hydrogen fluoride gas in water, it forms an aqueous solution. And remember, anytime you see AQ, that tells you that the solvent, the thing present in the greater amount in a solution, is water. And once HF gas becomes HF aqueous, we no longer name it as a regular binary compound because now it behaves as a binary acid. And the naming rule for aqueous binary acids say that you start with hydro to indicate the hydrogen, and you add the root of the nonmetal. So if we're dealing with fluorine, what you're going to do now is that you're going to drop the ending, and now you get fluoric. So putting it together, we get hydrofluoric acid. And a quick side note about acidity, we're going to do a full acids and bases deep dive in another video, but for now, just know this. Whenever you see a hydrogen written in the front of a nonmetal and the compound is aqueous, that means that you're looking at an acid. So when you drop hydrofluoric acid in water, it'll undergo an ionization reaction. In other words, it'll ionize or break apart into its corresponding ions, H plus and F negative. And if I really want to get specific about this, hydrofluoric acid is acidic because of the fact it ionizes into these hydrogen ions. And honestly, in another lesson, I'm going to do a whole deep dive on this, I promise. But in the meantime, hopefully this makes just a little bit more sense. Now, how do you name some of these other aqueous binary acids? Well, let's see. HI has hydrogen and iodine. So you take the word hydro for hydrogen and you drop the ending of iodine so that now you have hydroiodic acid. What about HCl? Hydro, then you take chlorine, drop the ending, and we get hydrochloric acid. What about HBr? Hydro, bromine, then you drop the ending, and now we get hydrobromic acid. And lastly, H2S, we name it hydrosulfuric acid, where the S comes from sulfur. Note that this is not hydrosulfic acid. Teachers love throwing that one in as a trick. It's hydrosulfuric acid. And remember, prefixes are not used when naming aqueous binary acids. So even if you see H2S, you don't call it dihydrogen sulfuric acid to show that there's two hydrogens present. No. We do not use prefixes here. Prefixes are only used for naming covalent compounds. Now, if you don't see an aqueous symbol and instead you see this gas symbol written next to it, then it's not a binary acid. You give it different naming rules as mentioned earlier in this video. So for example, HI is not hydroiodic acid, instead it's hydrogen. And then you take the second name, iodine, and you drop the ending so it ends in iodide. In a similar way, HCl gas is not hydrochloric acid. It's hydrogen. Then you take the word chlorine, you drop the ending, and you turn it into chloride. What about HBr? The same, hydrogen, bromine becomes bromide. What about H2S? Hydrogen, then sulfur, the ending drops, so now you get sulfide. And again, no prefixes here, so it's not dihydrogen monosulfide. No. It's just hydrogen sulfide. And two big exceptions that I just want to point out here is that just keep in mind that H2O, which is water, and H2O2, which is hydrogen peroxide, even though these start with hydrogen, they are not acids. So just keep that in mind. Now let's talk bases. One really easy way to identify a base is to look for the OH negative ion attached to a metal. And OH negative is a polyatomic ion called a hydroxide. And you see, it exists as a unit. When you put a base in water, it also undergoes an ionization reaction similar to how we talked about with the acids. A base will ionize into its metal ions and hydroxide ions. So for example, take NaOH. NaOH will ionize into Na plus and OH negative ions. And so the presence of these hydroxide ions is what makes the solution basic. So naming bases is actually super easy. All you're going to do is you're going to take the name of the metal and you're just going to tag a hydroxide at the end. So for example, NaOH would be sodium hydroxide. What do you think KOH would be? Well, K is potassium and it has an OH written to the back of the metal, so we're going to give it the name potassium hydroxide. What about MgOH2? Well, you see, that little 2 outside the parentheses came from magnesium's +2 charge. And again, if you haven't seen the last video that I posted about how to name ionic compounds, highly recommend you check it out because I talk about how to uncross charges when you're dealing with metal ions, so definitely give that a watch when you can. But anyways, magnesium always has a fixed +2 charge. So you don't need to write the Roman numeral to tell you the charge of magnesium because we know it's always going to be +2. So we give this the name magnesium hydroxide. The same cannot be said about this next one. You see, now you have CuOH2. Cu is copper, and copper is a transition metal. And most transition metals have variable charges, meaning you don't know what the charge is. You don't know if the charge is +1 or +2 or +3. So you have to tell the person what the charge is by writing a Roman numeral in parentheses next to the metal. And so when we look at this 2 likely came from the copper. And I say likely because I mentioned this in the last video. You have to be careful whether or not the formula was simplified or not. But I know this is not simplified because OH will always be -1. It's hydroxide. It's always going to be -1. And so when I drop this -1 and I cross it, I ended up getting this 1 here that you don't see because we don't write 1s as subscripts. But anyways, this 2 next to the OH likely came from the copper. And so what you can do is that once you figure out the charges, if you cross them and you end up getting the exact same formula that you started with, you know you're doing a good job. So the charge of copper is a 2+ charge. And so how you write this is copper, parentheses 2, to show that copper has a +2 charge and not a +1 or a +3, and then hydroxide after it. So again, the Roman numeral here tells you the charge of the metal, and you have to write it because the charge is not fixed, right? There's only a certain group of ions where their charge doesn't change. Like in the example here for sodium, sodium will always be +1 because it's in group 1 of the periodic table. K will always be +1 because it's also in group 1 of the periodic table. Magnesium's in group 2 of the periodic table and will always be a +2. So we don't need to write the Roman numeral 1 or the Roman numeral 2 for any of these because we know the charge doesn't change. And lastly, to end this lesson, NH4OH. This is unique because now you have two polyatomic ions written here. You have NH4+, which is ammonium. It's a polyatomic cation, meaning it has a plus charge. And you have OH-, which is a hydroxide. So when you crisscross these charges, that's why you get this 1-to-1 ratio, meaning for every one ammonium, you have one hydroxide present. So how do we name this? Ammonium hydroxide. Thank you guys so much for watching my channel. If you felt like this lesson helped, please don't hesitate to like, subscribe, comment down below. In the next video, we're going to move into naming other polyatomic ions, specifically oxyanions and oxyacids. And honestly, we'll see if I split that into